My topic today is about how to use quantum signal processing for beyond gate model system calibrations. And a series of joint work with Murphy, Jonathan, and Dong and Chris. Before I dive into details, I want to first talk about what's the kind of current paradigm of quantum computing. So current quantum computing basically falls into these three different paradigms. The first one is digital quantum computation, where you have a universal gate set that is discrete and finite number of basic gates. We want to synthesize a large functional circuits. And the second type is called analog quantum computation. We have a Hamiltonian system. We map our problem onto the Hamiltonian system. We control it, evolve it, and then we get the answer. And the third one is more like between these two polarizing sides. So it's a hybrid version of the digital and analog computations. Well, locally we have some kind of discrete digital gates, but we also integrate the unitary evolution that may represent some analog Hamiltonian systems into our computations. These two types of paradigms have their own advantages and disadvantages. For example, for the digital computation, we have a very well-developed calibration method, so it's very easy to be calibrated. But for the analog counterpart, there's no efficient way to calibrate the system, and it's very hard to calibrate. However, as a compensation, this analog system is a physical nature, so it's very easy to be operated. So it's it can be used to solve large-scale system using some limited resource, so it's resource efficient. But as a drawback of digital computation, we have to decompose our quantum circuit onto different gate sets, and that may give us a lot of overhead. And we also have to do error correction in order to ensure the high fidelity quantum operations. So in general, if we want to solve large-scale system computation, digital computation will be more expensive than analog computation. But this kind of comparison motivate us to consider how we can integrate the power from both sides. And this gives us the main idea of this talk. So if we dive into the details of this analog and digital computation, we may find at the lowest level, all of them are pulse controls, because we want to implement this basic gate set, the basic gates in the basic gate set by using the physical imputation. We have to use some pulse in order to either implement one operation or the second operation. But it's more like a modularity problem, because we want to implement some basic gates and then we logically combine them together to be a functional circuit. But for analog system, we have a whole system to control. So it's an entire system. We can use its evolution and physical property to solve problems. So the pulse control is more like a system-wide level. So it provides us more flexibility to control the system instead of just focusing on the modular parts. And in order to answer our previous question, we may ask an alternative question, that is whether we have a hybrid approach between gate-based computation and analog computation. And indeed, there's one example in gate-based computation called quantum signal processing. And the structure is like we have some local Z rotations, but we integrate the unitary evolution as some building block in order to transform the Hamiltonian information into some other targets. And this provides some insights for us to answer our question through the lens of quantum signal processing. Before we talk about how to bridge the gap, we have to first know what is quantum signal processing. And from the classical side, you have a signal, just as a projector. There can be some wave, sound wave or EM wave, and this wave brings some information to be processed. And in quantum setup, we also have something similar. So for example, our gate is a parametric gate set that is parametric, the parameters is literally just a theta and a phi, where theta representing some kind of information we want to process, but phi is a variable that we can tune to control our system. If we use this basic operation once, we may get something like a bump. But if we can combine them together in a product using our phi 0 theta, phi 1 theta, so on and so forth, we may get a complex sequence. And this sequence can implement some functional transformations. So take a look at the right panel. We see that if you have three different phases, we may get something that have a flat top. But if we can go even deeper, there's elegance of quantum signal processing says that we are able to implement universal function transformation to control the system. So if one day we can realize a very powerful quantum computer, we want to do machine learning on quantum computer, you may want to implement the activation function, and the elegance of quantum signal processing says that we are able to implement this activation function using this kind of sequence. And quantum signal processing just brings us ideas from the classical side to quantum size. So for QSP, for short, so we have a interleaving sequence. We have a zero rotation representing the modulation of the wave. We have X rotation carrying the information that is denoted by the variable X. And then we apply this zero rotation to, equivalent, we rotate the axis of the ball around zero rotation, and then we use our information, we send our information into the system, and then do the transformation. And just like the classical EM wave, this kind of interleaved rotation sequence give us something like transformation of the information. And that is a whole idea of quantum signal processing. And actually, quantum signal processing has its own feature. So it's a hybrid digital analog nature of the quantum signal processing. So it's like a digital computation because we have discretized the gates format, and we also have a fixed X rotation gates. But it's more like an analog computation because we have a continuous parametric class of gates to be queried in order to implement the universal control. And actually, the idea of quantum signal processing is originated from the MR pulse sequence control. So that also, shows that there's a kind of deep connection between quantum signal processing and analog computation. So QSP, originally we defined as single qubit rotation, but it can be lifted to the high dimension. We can literally just use our Hamiltonian as some upper left block of the unitary matrix as a core block encoding, and then we repeat the previous sequence, we're able to implement a function of the Hamiltonian. And this makes QSP host application for solving a variety of problems. For example, on the Hamiltonian simulation, we just transform H to be the exponential propagator of the Hamiltonian systems. And for linear system, we just invert all the eigenvalues for the Hamiltonian. And for many problems, we can literally just use the same paradigm to solve the problem. So QSP is credited to be a unified framework for a lot of quantum algorithms. And at the same time, although it's not only flexible, but also very optimal. If we compare our quantum signal processing method with other state-of-art quantum algorithms like product formula characterization or Taylor series expansion, in terms of quantum simulation, we find that quantum signal processing is one of the most, is almost the most efficient one that can attain the near optimal scaling in terms of query complexity. So it's optimal in terms of theory of big O, but it's not efficient enough because in terms of big O, we only consider what is the query complexity. But in order to implement it using the digital quantum computer, we have to first do decomposition and then have the circuit synthesis optimization. But this may introduce a lot of overhead and make our quantum signal processing application less efficient. And our talk today will focus on this main research question. So can we directly harness the hybrid digital and analog nature of quantum signal processing to bridge the gap between gate-based computation and Hamiltonian-based computation? Especially, we focus on the near future practical applications. And we can also ask ourselves, what is the most promising application in the near future or in the near term? So I think one of the most important applications is calibration and metrology, because we want to learn the property of the system. We want to characterize the system so that we can know how does it evolve and whether it can help us solve some more important questions. So to answer this question, I will break my talk into three parts. The first part, I will talk about the QSP-based phase estimation so that we are able to estimate some kind of phase or phase sequence in terms of the hybrid digital analog setup. And then I will dive into a more higher level benchmarking things by probing the system evolution and calibrating the Hamiltonian amplitude error. And then we will go to something that is even more closer to the scope of today's workshop, and we will get something that is purely analog. Okay, so for the first part, we want to do the phase estimation in the hybrid setup. So the problem is like this. It comes out from a practical setup because we want to accurately implement the CZ gate, which is 1, 1, 1, -1 on the diagonal. But actually, in the real production, we might have some unwanted swap angle. So for example, in Google setup, we have fermionic simulation gates. So in the single excitation subspace, we have a rotation that is not desirable, so that is theta, that makes the kind of single excitation basis. And we also have some phi that representing the phase difference between these two different states. In the prior arts, the main idea to calibrate this type of unwanted swap angle is by using something called amplification, because we want to amplify the error so that it can be read out in the final measurement process. And this will give us some kind of more resolution in order to do the calibration or learning, which will give us something called Heisenberg limit. And the circuit structure is very similar to, circuit structure is defined here, and it's a periodic circuit. So we have an SM gates containing some unwanted swap angle. We have the tunable gates to increase some kind of more functionality of these circuits and raise the power by repeating this sequence for d times in order to amplify this error, in order to amplify this theta error. And then we do the measurement to extract the information and do post-processing. So the post-processing is based on the measurement probability, and if we just plug out this measurement probability, we may find this highly oscillatory probability, which makes a lot of sense because it has a rotation, and once you have kind of 1,000 rotation, we get a highly oscillatory curve, for example. And this oscillatory curve makes the inversion of this complex relation to estimate parameters super challenging, because you want to indeed locate the highest peak, or to find the global minimum among a lot of local minima. And all of this previous process relies on the black box optimization, so it's an iterative method and noise sensitive. And it also relies on a condition called phase matching, because we don't want this phi angle to have the interference with our theta angle. So if we don't do the kind of tunable gates to the cancellation, they might couple together to undermine the accuracy of the estimation. And we also have this D is required to be 1 over theta. That is because we have to make this result more and more accurate and follow the Heisenberg limit scaling. And when theta is equal to, for example, 10 to the -3, that means we have to use thousands of gates application in order to do the calibration. That's not affordable, especially for the near-term applications. We can ask why we get this kind of challenge by using the prior arts. So it lies majorly into two faults. So the first fault is due to the phase matching. Because I said before, if phi is not equal to 0, it might have some coupling effects between our theta angle. And we can take a look at this Fisher information. If phi slightly deviates from 0, then the Fisher information will quickly drop to almost 0 and fully undermines the statistical power of our inference. And for the right-hand side, it's more like a practical challenge for us to do this inversion of the highly oscillatory probability. So once our number of gates become larger, we have a lot of local minima in this very narrow interval. And it makes it super hard for us to solve this problem practically in order to get this theta estimator. So to conclude, we want to get rid of two different challenges. One is phase matching condition, and the second is the black box optimization. And that is the motivation for our research. And our method is to do the metrology using quantum signal processing. So if we take a look at this 2x2 unitary as the FSIM gates representation, we'll find there's a two-dimensional invariant subspace. And by getting this out, we can write it as R phi of theta. So this is a single qubit unitary, and this process is called qubitization. And for the qubitized, in this qubitized subspace, we can insert a tunable zero rotation in the system and to form an interleaved sequence. Then for this sequence, we get structures that are very similar to quantum signal processing, especially in this two-dimensional subspace. And as we said before, this output probability will become an oscillatory polynomial internal trigonometric functions in different angles. But the nice thing here is we show that we are able to separate the theta and phi angles in the Fourier space. So if we perform the Fourier transformation of the probability, we can actually turn all the phi and chi dependency into the phase, but leave the theta dependency in the amplitude. And this nice separation will separate the coupling issue we talked before and to resolve this phase matching issue. And alongside, we can discuss what is our workflow of the quantum signal processing phase estimation. We start from different circuits with different omega angles, and then we collect all the measurement information in order to characterize the polynomial of our interest. We pass everything in the Fourier transformation to focus ourselves in the Fourier space. So from the right panel, you can see that in the real space is a highly oscillatory curve, but in the Fourier space, there's a very special pattern. For example, for the positive Fourier modes, they were concentrated around the theta value. So that enables us to perform the linear regression to direct extract information instead of solving an iterative optimization problem that is very easily stuck as local minima. And by this discussion, we see that two challenges has been resolved. And we also did this study, and we showed that our method is optimal in terms of data post-processing because of the agreement with the Kramer lower bound. That literally means that there's no room to improve our data post-processing. And it's also near optimal in terms of initialization measurements because of the agreement with the quantum Kramer lower bound after factor 2. The reason for us to get a factor 2 is because we use Bell states. So Bell states are in pairs. We have X and Y. So there's a kind of redundancy in terms of initialization, but the use of the Bell states is to simplify the post-processing because we don't want to do optimization. We want to do linear regression. And we also deploy our method on the Google's quantum device, and we see that our method is super accurate. So it increases 2-qubit gate learning accuracy by two orders of magnitude. That is justified by the numerical results here. So if we put our eye on this kind of results, we see that our method have a variance of magnitude 10 to negative 8, but Google's previous prior arts cross entropy benchmarking have the variance of magnitude 10 to negative 4. So our method have a huge improvement against the previous one. And we also, our method is also very efficient because originally SCB requires 100 of gate applications, but now we only need 5 different individual gates to achieve this 10 to negative 8 accuracy. Okay, and to the first part, we discussed how to do this quantum signal processing phase estimation in terms of hybrid analog digital computation because of the continuous parametric fermionic simulation gates. But now we can dive into something that's higher level, that is a benchmarking of the Hamiltonian dynamics that may represent in the analog evolution. The conventional paradigm of quantum signal processing introduced a lot of trash because we want to transform the Hamiltonian as the upper left block of one matrix to the upper left block of another matrix with a function that is acting on this Hamiltonian. But all the other parts are highly likely non-zero because the unitary matrix. But this part are thrown away in the conditional paradigm, either using amplitude amplification or measurement repetitions. But this information may possibly contain some information that can be reused to boost our computation. So in order to convert this trash into the near-term treasure, we want to investigate whether we are able to get a more generalized quantum signal processing in order to follow the classical paradigm of repetition or amplification. And formally speaking, if you just apply a quantum signal processing circuit onto a quantum states, you will separate into two parts. The first part representing the action of Hamiltonian on the state. For example, if it's a time evolution, then it's time evolution. If that is a linear system, then there's H inverse. But this success is flagged by the ancilla qubit states of all 0, and all other measurements we are called garbage in the standard literature that representing the failure of the quantum circuit. And it will contain some undesired basis transformation and makes the reuse of quantum information very challenging. But we still want to ask whether we are able to get a correction map so that we can convert the failure into success and boost the utility, boost the utilization of our computational power, especially benefits for the near term. And luckily, we get some pretty interesting results, even though the problem is super challenging. By carefully design a protocol of this failure correction, we're able to convert the original failure samples into something successful. So if, for example, if in this one step for quantum signal processing here, if the first measurement gives us 1, that means the first step is a failure step in the conventional sense. But next time we do the initialization to access the next round of applications, and by using some carefully designed protocol, we are able to show that if we measure the first at 0, but next at 1, first at 1, next at 0, we are able to get 1 minus f squared acting on this Hamiltonian H. So imagine if f is a projector, then 1 minus f squared is also projected but onto the supplementary subspace. The complementary subspace. And then these two projectors will form a pair of classification problems. So if we just imagine we're on the decision tree, we can first apply this circuit on some energy gap, and then we separate our Hamiltonian into 2 different sub-Hamiltonians, and we do this so on and so forth in an adaptive sense. Then we are able to fully classify our quantum states. In terms of application, we show that feed-forward quantum circuit can hold a fundamental advantage against algorithms without feed-forward. For example, in our quantum state classification problems, we achieve an exponential speedup in terms of number of bands by using the feed-forward quantum algorithms. Okay, and we also want to use this feed-forward idea to revolutionize the benchmarking, because the original benchmark is like we populate our gate operations on different qubits, and at the end of the operation, we measure all the qubits to get the information. But now we want to have something that is more elegant. We run the circuit coherently, but measure some intermediate ancilla qubits with some resets. And this introduces 2 ingredients in our algorithm. The first one is called the feed-forward, because our next initialization depends on previous measurements. And the second ingredient is called cosine sine decomposition. That is a universal representation to write a unitary in terms of the single value of the upper left block. And this is universal, so it is applicable for analog computation. Our unitary can be an analog dynamics instead of just a kind of composition of digital gates. And if we think about the probability of measuring the sequence of outputs S1, S2 to Sk, then this probability is very similar to a multinomial distribution that is similar to the Gaussian board. But the only difference is the actual distribution will depend on the statistical property of the random ensemble instead of just a deterministic value. And for each measurement, we can also investigate what's the fidelity in the system, because our fidelity is defined as the weight of the true component in the computational process. So it's a linear combination coefficient between the exact probability and the noise probability. By inverting this defining equation, we're able to calculate the alpha by using the S samples as different steps. And this, after the first measurement, we get alpha 1, that's representing the fidelity after applying 1 analog operations. And after the second one, we get the alpha 2, which means the accuracy after we apply the second analog applications. And in order to, this evolution trajectory actually tells us something very important. We are able to see what is the capability of our analog quantum computer in order to solve large-scale computation problems. But if we want to learn this sequence in the conventional setup, we had the first round circuit of steps 1, and then run circuit at step 2 and 3, so on and so forth. This means that we have to restart the computation at the very beginning, and instead of reusing the information from the previous round. However, our feed-forward quantum circuit holds the potential to revolutionize this paradigm, because for example, you want to learn alpha k plus 1, all the previous measurement can have the power to facilitate the learning accuracy of the next round. So it will give us something that is very fancy, because we only need one pass to learn the sequence instead of start from the very beginning. So our method, in order to learn the sequence, we only need OK operations instead of OK square operations in the conventional setup. And we can also consider to use the random bosonic or fermionic dynamics to do the benchmarking, or to learn the evolution trajectory that is representing the Hamiltonian amplitude error in this analog setup. And we can move to the next part. That is because that is more exciting. We want to focus on a pure analog setup, and we can directly jump out from the previous hybrid digital analog setup. And in this part, I will talk about how to use quantum signal processing to learn an analog pulse control map. In the control of analog systems, or in most quantum application, we can see there's a very important component called DAC. This is a digital to analog converter. It will convert your digital piecewise constant sequence into something into some continuous sequence of the analog signal. But actually, DAC is for all the applications bandwidth limited because of this kind of piecewise constant approximation. We are able to approximate our kind of analog pulse sequence by using a piecewise approximation. And this kind of inspire a new paradigm of learning analog pulse controls, because they divide into 3 different steps. For analog signal, we first do the discretization. We try to make a piecewise constant counterpart of our analog signal. And for the piecewise constant analog, we get in this hybrid signal we get an interleaving sequence, but with different phi values, because phi is now actually representing the average value among on each interval. So originally we have a continuous curve, but we can do the average on each interval to make it discretized. And then we learn to discretize the hybrid signal version of our original analog problem. By learning this sequence phi 1 to phi L, we are able to reconstruct our original continuous signal by a conversion process. So unlike the previous introduced quantum signal processing phase estimation, there's a major difference here, because we don't have a periodic structure. So because we cannot guarantee that the average on each interval is the same. So after the discretization, our signal may be something that jumps back and forth. And this breaks the periodic structure, but it's still very structured, because this representing the trigonometric polynomial. Trigonometric polynomial, and give us something called Laurent polynomial structure. And by studying this Laurent polynomial structure, we are able to infer this phi 1 to phi L from the experimentally measured results. And this problem has been investigated in the classical, in the standard quantum signal processing phase estimation literature. And all we have to do is to sample our kind of discretize the signal evolution on the uniform distributed theta angle to characterize this polynomial, and then we pass it to the Fourier space and to do the analysis. Okay. As a conclusion of today's talk, so we have show that the quantum signal processing idea is very useful to bridge the gap between analog computation and digital computation. And back to our original paradigm, we see that we indeed say that this gap can be bridged by using quantum signal processing. And we show you a wide range of examples that we can use quantum signal processing to improve both calibration and programmability of analog computation or in the hybrid setup. As a future outlook, there are a lot of potential research we can pursue along this way. So the first one is whether we can learn and calibrate quantum errors using quantum signal processing. We show that the unwanted swap angle can be calibrated, but there might be some other promising research that can, or noise model can be incorporated into the quantum signal processing framework. For example, in the in the stabilizer code, we have the representation of the unitary as a stacking of different projectors, and it actually coincides with the idea of block encoding and quantum signal processing. So we might be able to incorporate this surface code structure into our QSP framework. And the second possible direction is whether we can integrate error correction routine into the quantum algorithm design. Because in the previous, in the standard literature and in the conventional practice, we always first run either an error correction or quantum algorithm, and then we run a quantum algorithm to get accurate results. So there's a kind of sequential operation, but now we can integrate them together into a single process in order to improve the accuracy and efficiency of the near future quantum computation. And we might use some kind of paradigm to conceptualize our ideas. Like we can first apply quantum circuit, we do some measurements, and the measurement may contain some information that's very useful, and we can use classical computer to process information and design the optimal control policy so that we can improve the computation in the next round. And I would like to thank you for your attention to this talk, and also thanks for my collaboration, Murphy, Jonathan, Don, and Chris. And I'm also on the academic job market this year, so if you have any wonderful opportunities, I would very appreciate to reach out to me. Thank you.
All right, thank you for a very nice talk, and we have time for some questions.
Very nice results. So on the phase estimation, you have a figure with the feature information versus the parameter, which is sharply peaked. But so your protocol, like compared to this, do you have a plot where your protocol is also on this, like feature information versus the angle?
Yeah, that is a very good question. So actually our method, because we don't have this kind of phi issue, so by using a similar calculation, our method attains almost as a peak. So there's
it's constant across all phi angle, or?
Yeah, because we have a separation between different phi angles.
I see. Okay.
Yeah.
Thanks.
Thank you.
More questions or comments?
Yeah, thanks. I think maybe I missed it, like in the feed-forward QSP, like, is there a fundamental limit on how well this approach can perform compared to, like maybe not compared, but like just like, you show there's improvement, but is there like a limit given like certain functions? Maybe I just missed it.
Yeah, thanks. That is a very that's a very good question. And for some kind of universal control setup, it's very hard to say what is the limit because we have to establish the lower bound. But for this classification problem, I think the lower bound is log L because we can justify if there's not log L, then we are not able to cover all these bands in the in the classical algorithm setup.
Thanks.
Yeah.
Any more?
What's the intuition you analyze? So in the first part, what's the intuition you analyze the gate parameters in the Fourier space that allows you to separate the parameters? So I wanted to sort of understand that a bit more.
Yes. Yeah, so actually the idea is because in the Fourier space we are able to separate these kind of phase angles because it originally appears as a e to the I phi components. And the cosine and sine are more like an amplitude of this. So my original intuition is like I can try to do the analysis to see whether I'm able to get a pretty nice separation. And actually the outcome is positive because we have the separation, but as a very interesting aside, we also have a concentration of the values that enables the linear regression instead of doing the optimization of inverse relation.
Okay, I see. Thank you.
Thanks. Thanks for the talk. And I'm curious about, like, you mentioned that you use a Fourier space, then you can separate these parameters, and then you can kind of like infer back these two parameters very easily. I'm curious about whether you have quantitative analysis on how many shots you need to take in order to get that. Things like, you can imagine that if you do not have very accurate estimates of the probability for these parameters, they may like scramble out between each other.
Yeah, that is a very good question. So we have a quantitative analysis. It's also rigorous mathematical proof to, because I'm from math department before, so to justify that when the number of samples scale as or the variance of this inference scale as 1 over m times d squared times theta whatever. So you can check the paper for details. And I can also show there's a kind of there's a GIF I can show you. Sorry. Oh yeah. So if we take a look at this evolutionary curve, you can see that when the number of samples become larger, you indeed have some kind of jump back and forth, but in the Fourier space, it remains almost bounded, where almost concentrated when the sample size is getting larger. Yeah, and the concentration is also showed in the previous figure. So you can see that if we just increase the number of these, then we can see that it's almost bounded for the positive Fourier modes. But for the negative Fourier modes, it's of a very small magnitude. Yeah.
Any more questions? Okay, let's thank both our speakers again.